In this video, we'll explore outliers and obvious errors. This is a box plot displaying the distribution of some simulated data. If this is the first time you're seeing a box plot, the idea is pretty simple. Values are represented along the x-axis. The box in the middle represents the middle 50% of values. The thick black vertical line in the center of the box is the median. The lines extending horizontally out from the box capture all but the most distant values. Then any values beyond a certain distance from the majority of the data are represented as single points. Now, I've purposefully added some extreme values or outliers to the data, and these values are clearly represented as standalone points, 2 to the right of the box and 1 to the left. In the real world, outliers may be caused by a number of different things. They may represent extreme but perfectly valid measurements, such as a human being who is more than 100 years old. They could be caused by variability in measurement due to imperfect equipment. They could be caused by experimental error, or even something as simple as a mistake when entering data into a computer spreadsheet. As the data scientist, it will often be your job to figure out why there are outliers in the data. Depending on what you find, they may be discarded or retained, and this decision could have a significant impact on your final analysis. Looking back to the box plot example, how do things change if I told you these values represent the ages of people? Well, the extreme value all the way to the left is less than 0, so something must be wrong. This is a case of an obvious error in the data because there's no such thing as a negative age. So errors may appear in many forms, including values so extreme that they can't possibly be plausible. For example, a person aged 243 years. Or values that simply don't make sense, like the one we just saw. As with outliers, it's important to assess the cause of errors in the data. They may be caused by measurement error, data entry error, or they could even be intentional if, for example, the person entering the data was sinister enough to use something like -1 to represent a missing age. Bad idea. In most cases, the obvious errors should be removed or replaced. I've simulated another small data set here called df2, which contains some normally distributed variables plus a couple of extreme values. We can use summary to quickly see that the value of 500 is extreme relative to most other values in column B, and that there's a negative value in column C. But our view of the distribution of values in, for example, column B is limited in the summary output. For a more complete view, we can view a histogram of B using the hist function. Here, it's clear that all values are concentrated well below 100, but that there's a single value up at 500, suggesting that perhaps an extra 0 was accidentally added to what should have been a 50. Notice in the call to hist that we can control the number of buckets or breaks into which the data are broken up with the breaks argument. Here, we apply a box plot to the full data set df2. R conveniently generates a box for each column of the data. Again, we clearly see the extreme value of 500 in column B and the negative value in column C. Let's get our hands dirty with some extreme values.